now, across the globe, governments and private markets are just spending billions of dollars obsessing over electric passenger
Oh,
cars.
yeah. It's the dominant conversation everywhere.
Right. I mean, we constantly talk about the brands, the range, the charging speeds, the styling. But, well, what if I told you that in 2025, despite all that massive cultural and financial attention, passenger cars represent only about 2% of the global vehicle fleet by unit count?
Kind of a staggering number when you hear it out loud, just 2%.
2%. So we are essentially ignoring the vast majority of the transportation economy,
Right.
the actual machines that move the physical weight of the world.
Exactly. And, the smartest investors and strategists, they know that focusing solely on that 2% is a massive vulnerability. It fundamentally distorts how capital is allocated.
Because we're making assumptions based on a tiny slice of the pie.
Right. When you step back and look at the actual physics of global mobility, the
Mhm.
logistics networks, the surface mining operations, the transoceanic shipping routes, the popular narrative completely shatters.
The narrative being that we're just going to swap every single internal combustion engine for a lithium-ion battery and call it a day.
Yeah, that narrative. It's a fundamental misreading of how heavy industries operate, how their margins are constructed, and honestly, what the laws of physics actually permit.
And that is the exact premise of our investigation today. So welcome to the deep dive. Today, we are stepping into the shoes of a corporate strategist or, an institutional investor or policymaker looking at a 20-year horizon.
A very critical perspective to take right now.
Absolutely. The core mission of this deep dive is this. If you had to allocate billions of dollars of capital in the transportation transition, where would you actually place your strongest strategic bets? Because the answer is far more complex than just building a bigger battery factory.
To even begin answering that question, we have to deliberately pull our focus away from the consumer driveway. The foundation for our discussion today is the Global EV Outlook 2026, alongside a suite of internal strategic dossiers that specifically look at frameworks for capital allocation in this electrified transport economy.
And those dossiers, they start by pointing out a truly staggering statistic. In 2025, over 20 million electric passenger cars were sold globally.
Which is an undeniable milestone.
It is. I mean, that is roughly 25% of all new car sales worldwide, with China alone accounting for about 13 million of those units. But it creates this massive blind spot for us.
Yeah, because of that sheer volume, we just assume the passenger car model is the blueprint for everything else.
Exactly. Industry analysts actually have a specific term for this cognitive bias. They call it the telescope effect.
The telescope effect.
Right.
Because passenger cars are highly visible. They sit in our neighborhoods. They are deeply tied to our personal identities. They're heavily subsidized.
Then debated in mainstream politics constantly.
Constantly. And because of that extreme visibility, they capture roughly 90% of public and media attention.
So we are essentially looking through a telescope at this one brightly lit, highly specific fraction of the mobility landscape. And we're assuming the rules of that tiny fraction apply to the entire universe of transportation.
Which blinds us to the sectors that actually carry the massive structural capital and emission stakes. We're talking about commercial long-haul trucking, commercial aviation, deep-sea shipping, heavy industrial machinery.
Right. If you are an executive or an investor, letting the narrative of consumer EV adoption dictate your understanding of the whole energy transition is basically, a fast track to misallocating billions of dollars.
Totally. Because consumer vehicles and heavy industrial transport, they operate on completely different economic realities.
A consumer buys a car for convenience, right? Status, maybe an occasional road trip.
Yeah, but a commercial vehicle is a highly optimized capital asset. Its only purpose is to generate revenue by moving mass across a distance continuously.
So to truly understand where the transportation economy is going, we have to abandon the telescope and look at the structural physics of how things actually move.
Exactly. We stop looking at the brand names, and we start looking at the physics and unit economics.
The strategic dossiers introduce a really rigorous, multidimensional framework to judge a sector's readiness for electrification. It strips away all the environmental ideology and the marketing.
It doesn't ask, is this vehicle green?
Yeah.
It asks questions about 5 specific dimensions.
Let's walk through those.
Sure. You have energy density requirements, the payload penalty, the utilization profile, downtime tolerance, and infrastructure dependency.
And this framework is essential because it forces you to look at the total cost of ownership, the TCO, and the physical realities of the duty cycle.
Right, so let's break those dimensions down. The energy density requirement is simply how much energy you physically need to carry on board to complete a typical route without refueling.
Makes sense. And then the payload penalty.
The payload penalty is the critical financial metric. If we replace a relatively light diesel tank with thousands of pounds of batteries, how much revenue-generating cargo do we have to leave behind on the dock just to stay under legal weight limits?
Wow, yeah. And then you have the operational side.
Yes, the utilization profile asks whether the vehicle runs for 2 hours a day, like a commuter car, or 24 hours a day, like a mining truck.
Okay. And downtime tolerance.
That evaluates whether the underlying business model can survive the vehicle sitting idle for hours to charge, or if every minute stopped is literally destroying the profit margin.
And finally, infrastructure dependency.
Right, which asks if you can actually secure the massive megawatt-scale grid connection required to charge these heavy assets right in the location where they operate.
So when you apply that specific physical and financial framework, it immediately highlights what the dossiers call the uncontested BEV victories, the sectors where battery electric vehicles genuinely and decisively win.
Urban passenger cars are the obvious one, but also 2- and 3-wheelers.
Oh, yeah. If you look at the global data, electric 2- and 3-wheelers are actually the fastest scaling mobility segment on Earth, right? Especially in India and Southeast Asia.
They are scaling rapidly because the physical constraints of those vehicles perfectly match the current capabilities of lithium-ion technology. Think about an electric scooter used for delivery in Mumbai.
The energy density requirement is incredibly low.
Exactly. And the payload penalty is non-existent because the battery is small and the cargo is light.
The same logic applies to urban delivery vans, right? Like Amazon, FedEx, DHL. They are electrifying their urban fleets aggressively.
Because the urban delivery duty cycle is fundamentally a low-speed stop-and-go route. They travel maybe 50 to 80 miles a day on a highly predictable schedule.
And the cargo is usually parcels, which take up a lot of volume in the back of the van, but they aren't incredibly heavy. So again, no payload penalty.
Crucially, they have immense downtime tolerance. The van returns to a centralized depot at 6 p.m. and just sits there for 12 hours overnight. It is the perfect scenario for slow, managed, low-cost charging.
But applying this framework to different industries yields some completely counterintuitive results. There is one example in the research that completely caught me off guard.
The mining equipment.
Yes, the dossiers highlight underground mining equipment as a massive near-term victory for battery electric vehicles.
That's a great example.
But underground loaders and haulers are massive, incredibly heavy pieces of machinery working in brutal conditions. Why would that be an economically advantaged environment for a battery?
It's a brilliant example of how you have to look at the entire operational ecosystem, not just the vehicle itself. In underground mining, the single biggest operational constraint and one of the largest ongoing OpEx operating expenditure costs isn't actually moving the rock.
What is it then?
It is moving the air.
Oh, because of the diesel exhaust.
Exactly. Large diesel engines operating miles underground produce massive amounts of toxic exhaust and particulate matter. To keep the miners alive and meet safety regulations, mining companies have to install, power, and maintain colossal, highly energy-intensive ventilation systems.
Pushing fresh air deep into the shafts continuously, that must be incredibly expensive.
It is. So when you swap the diesel engine for an electric motor and a battery, you eliminate the tailpipe emissions entirely at the point of use.
Ah, I see. And by doing that, you drastically reduce the required capacity of those massive ventilation fans.
Yes. The reduction in the energy bill, just from running the fans at a lower capacity, is so profound that it completely alters the total cost of ownership calculation for the mine.
So even if the upfront CapEx, the purchase price of a battery electric loader is higher, it pays off.
Much higher, usually. But the OpEx savings on ventilation are so large that the BEV becomes structurally and financially advantaged almost immediately.
That is fascinating. The competitive advantage isn't found in the vehicle's performance, it's found in the ambient environment it operates in.
Precisely.
But looking at these successes, the scooters, the delivery vans, the underground loaders, this is where I think a lot of people, including some tech investors, make a very natural but dangerous leap in logic.
How so?
Well, we look at the cost of lithium-ion cells dropping over the last decade. We look at the energy density improving, and we think, well, if battery tech is moving this fast, let's not overcomplicate it. Just wait a few years, stick a giant battery in every single truck, ship, and plane, and call it a day.
And that exact intuition, trying to scale up smartphone battery logic to global heavy freight, is what leads billions of dollars of capital astray. It fundamentally ignores the payload penalty.
Right, let's look at the mathematics of a long-haul logistics network. A Class 8 semi-truck operating on an interstate highway has a strict, legally mandated maximum gross vehicle weight. In the U.S., I think it's typically 80,000 pounds.
Yes, 80,000 pounds. And that weight limit includes everything: the tractor, the trailer, the fuel, and the cargo.
Wait, so if a diesel engine and full tanks weigh, say, 5,000 pounds, and you swap that out for a battery pack large enough to haul an 80,000-pound rig for 600 miles, that battery pack is going to weigh significantly more than the diesel system, right?
Substantially more. Depending on the chemistry and the desired range, a long-haul truck battery can weigh between 8,000 and 14,000 pounds.
14,000 pounds. So because you are capped at that 80,000-pound legal limit, every single extra pound of battery you add to the chassis is literally a pound of paying cargo you have to remove from the trailer.
Precisely. If a fleet operator buys that battery electric truck, they have to go to their customer and say, "I can move your freight, but because my truck is so heavy now, I have to leave 10% of your pallets on the dock."
That mathematically destroys the business model. I mean, the margins in freight are incredibly tight.
Extremely tight.
The revenue from the first 80 or 90% of a trailer's load is just covering the fixed costs, the lease, the driver's salary, the insurance, the energy. The actual profit for the trucking company is entirely contained in that last 10% of the cargo space.
If the battery consumes that capacity, the profit just evaporates. Which is why a one-to-one replacement narrative is a fallacy. You cannot just swap the powertrain without fundamentally rewiring the unit economics of the business.
Okay, so the payload penalty creates a massive barrier for heavy highway freight. But before we even dive deeper into how long-haul trucking solves that, the dossiers point out that we haven't even fully solved the easy wins yet.
The passenger cars and the urban delivery vans.
Yeah, because there is a hidden, massive complexity lurking right in our own neighborhoods. The electrical grid itself.
The electrical grid is the invisible gating infrastructure that will dictate the pace of this entire transition. It doesn't matter how cheaply we can manufacture vehicles in China or Europe if the local distribution grids cannot physically deliver the electrons to the vehicles where they are parked.
And the research here from the Argonne National Laboratory goes incredibly deep into this exact bottleneck. They've been conducting mesoscopic modeling for BEV fleets to figure out exactly how the grid is going to handle millions of unpredictable human beings plugging in their cars.
It's an incredibly sophisticated approach to a very chaotic problem.
When I first read about this, the scale of the data they're processing is just staggering.
Oh, absolutely.
Yeah.
Because if you want to predict grid stress, you can't just take the total energy required for 1,000,000 cars and divide it evenly across 24 hours. That's a macroscopic view. And it's useless because human behavior isn't an average. People all come home and plug in at the exact same time.
But conversely, trying to model every single individual driver a microscopic view is computationally impossible.
So they use mesoscopic modeling, the middle ground.
Okay, how does that work?
The researchers start with massive data sets from the National Household Travel Survey, the NHTS.
Yeah.
They use actual real-world data on when people leave for work, how far they drive when they arrive home, and how long the vehicle sits parked.
And they take this massive data set and group the vehicles into subfleets based on their physical properties and behavioral schedules.
Exactly. So one subfleet might represent suburban commuters who drive 30 miles to a corporate park, leave the car there for 9 hours, and drive home at 5 p.m.
And another subfleet represents local delivery vans making 80 short stops between 8 a.m. and 4 p.m.
Right. And once they have these subfleets, they run Monte Carlo simulations. This is a mathematical technique that uses random sampling to account for the inherent variability and chaos in human behavior. It runs thousands of scenarios to figure out the probabilistic peak load on a local grid.
It's essentially running a highly granular stress test on the local infrastructure. Like, what happens to the specific neighborhood transformer if all the suburban commuters arrive home between 5:30 and 6:30 p.m. and immediately plug in their cars?
And what the Argonne modeling definitively proves is that if we rely on what they call uncoordinated immediate charging, meaning every car just starts pulling maximum current the moment it is plugged in, the local grid loads become catastrophically severe. Yeah, the distribution transformers, which were sized for the energy demands of the 1990s, will literally overheat and fail.
So the solution isn't necessarily digging up every street in the country and laying thicker copper wire. The solution is software.
The transition from internal combustion to electrification is fundamentally a transition from hardware to software. The Argonne researchers modeled the impact of delayed or smart charging strategies. If the vehicle and the charger can communicate with the grid, the software can stagger the demand.
So like I get home at 6 p.m., I plug in my car, but I don't actually need to leave for work until 7:30 a.m. the next day.
Exactly. The charger communicates with the local utility,
Mhm.
recognizes that the grid is currently peaking because everyone is cooking dinner and running air conditioners, and it says, okay, we will wait. We won't pull any power until 2 a.m.
When grid demand is incredibly low, and perhaps when local wind turbines are generating excess power.
By using software to shift the charging window, you dramatically flatten the demand curve, protecting the existing physical infrastructure. But the modeling gets even more granular than that.
It does.
Oh, yes. To accurately predict the grid impact, the researchers have to simulate the physical chemistry happening inside the battery cells themselves during a recharge event.
The dossiers mention they use equivalent circuit battery models for this. It factors in the internal resistance of the cell and its open circuit voltage based on its state of charge. Let's break this down.
Sure.
Because I think people assume a battery charges like you're filling a bucket with water, like a steady, constant flow until it's full.
No,
But physically, chemically, that is not what happens at all.
not at all. Think of the lithium-ion battery's internal structure. The anode like a rigid crystalline lattice. It has highly specific, rigidly defined spaces where the lithium ions need to intercalate or lodge themselves during charging.
Okay, so when the battery is nearly empty at a
Yeah.
low state of charge, there are plenty of empty spaces.
Yes. The charger can push a massive amount of current, a high voltage, and the lithium ions easily find a home in the lattice.
This is why an EV charges incredibly fast, from 10% to 50%.
Exactly. But as the battery crosses, say, 80% state of charge, that crystalline lattice is mostly full. The internal electrical resistance rises significantly.
So if the charger continues to push high current at that stage, the lithium ions can't find empty spaces fast enough.
And instead of safely entering the lattice, they start piling up on the surface of the anode as metallic lithium.
Which is known as lithium plating, right?
Huh.
And that permanently degrades the battery capacity and can even lead to short circuits and thermal runaway.
Right. To prevent lithium plating, the vehicle's battery management software heavily throttles the charging current as the battery gets closer to full. This means a vehicle charging from 10 to 50% draws a completely different electrical load signature from the grid than a vehicle charging from 80 to 100%.
Wow. So when you multiply that highly variable chemical reality by millions of vehicles, the grid sees a constantly fluctuating demand profile.
The Argonne models factor in all of this chemistry, and they even differentiate between pure battery electric vehicles and plug-in hybrids, because the different battery sizes and usage patterns create entirely distinct load signatures.
The sheer complexity of just managing the light passenger vehicles in an urban environment is astounding. You have to perfectly orchestrate human behavioral patterns, local transformer capacities, wholesale energy market pricing, and the microchemistry of lithium-ion lattices all in real time.
And that is the easy part of the transition. That is the part of the mobility landscape that is structurally advantaged for electrification.
Which brings us to the real battleground, because once we leave the predictable, low-speed urban environment and we hit the interstate highway with heavy freight, all those constraints we just talked about are magnified exponentially.
This is where the transition gets incredibly difficult. The research draws a very sharp strategic line within the trucking industry itself. The divide sits roughly around the 400-kilometer mark.
Okay.
For regional and medium-haul trucking routes operating within that 200 to 400-kilometer radius, battery electric trucks are actively and successfully scaling.
Because they operate on a hub-and-spoke model. The truck runs a heavy load out to a distribution center, but it stays within range of its home base.
Meaning it can return to a centralized, privately owned depot to charge overnight, much like the delivery vans. The infrastructure dependency is localized, and the payload penalty is manageable over shorter distances.
But long-haul, heavy trucking moving freight continuously over thousands of kilometers is where the physics and the economics become ruthlessly unforgiving.
We discussed the payload penalty earlier, but in long haul there is a second constraint that is equally damaging: the charging time versus revenue hours equation.
Right, because long-haul trucking isn't just about weight, it is fundamentally a business of time. In heavily regulated markets like North America and the European Union, there are strict hours of service regulations.
A driver can only be legally behind the wheel for a set number of hours before they are mandated to stop and rest.
And an asset that costs hundreds of thousands of dollars only generates a return on investment when its wheels are turning. If a driver has to pull over and sit at a charging station for 3 or 4 hours in the middle of their shift to replenish a massive battery,
Those are lost revenue-generating hours that the fleet operator can never legally recover. The driver's shift expires before the freight reaches its destination.
which sets up what the strategic dossiers identify as a genuine, high-stakes, two-horse race for the future of long-haul logistics. Battery electric versus hydrogen. Both pathways have massive corporate backing, and they offer fundamentally different value propositions to the fleet operator. Let's explore the case for BEVs and long haul first.
The strategic argument for battery electric Class 8 trucks hinges on energy efficiency and operating costs. The tank-to-wheel efficiency of a battery system is extraordinarily high. Roughly 80 to 90% of the electrical energy pulled from the grid goes directly into turning the wheels.
That's incredible.
Because of that efficiency, electricity, especially if sourced from renewables during off-peak hours, is significantly cheaper per mile than diesel.
And to solve the downtime issue, the industry is racing to deploy megawatt charging systems, right? These are chargers capable of pushing such a colossal amount of energy over a megawatt of power continuously that they can theoretically recharge a massive long-haul battery in the 45 minutes that a driver is legally mandated to take a rest break anyway.
If you can synchronize the charging time perfectly with the legally required downtime, you theoretically eliminate the revenue hour penalty. But that requires a massive build-out of ultra-high-capacity grid connections at every single truck stop along the interstate highway system.
Which is a staggering capital infrastructure challenge.
Yes, which opens the door for the competing pathway. Hydrogen, specifically hydrogen fuel cells, and in some applications, hydrogen internal combustion engines.
The primary strategic argument for hydrogen is operational speed and payload preservation, I assume.
Hydrogen essentially preserves the operational logistics model that the freight industry has optimized for the last 70 years with diesel. Refueling a hydrogen heavy-duty truck takes roughly 10 to 15 minutes. It completely protects the driver's revenue hours.
And furthermore, hydrogen gas, even compressed in heavy tanks, and the fuel cell system itself weighs significantly less than a long-haul lithium-ion battery pack.
Meaning you drastically reduce the payload penalty. You don't have to leave the customer's freight on the dock.
But there's a catch, right?
The drawback is efficiency. Creating green hydrogen, using renewable electricity to split water via electrolysis, compressing the gas, transporting it, and then running it through a fuel cell on the truck to create electricity again, involves massive thermodynamic energy losses at every step.
You might only get 30 to 40% of your original renewable energy back to turn the wheels.
So hydrogen trades energy efficiency for operational efficiency. It costs more per mile in energy, but it preserves the payload capacity and the time.
And the industry is placing massive bets on this. The dossiers highlight a joint venture called Cellcentric, which I find strategically fascinating. It's a partnership between Volvo Group, Daimler Truck, and Toyota.
These are companies that normally fight tooth and nail for every fraction of a percent of market share.
Exactly. Yet they are joining forces and pooling capital to develop and mass-produce hydrogen fuel cell systems for heavy trucks.
It is a textbook example of ecosystem strategy. The capital required to develop hydrogen fuel cells and build out the refueling infrastructure is so massive that no single OEM original equipment manufacturer can shoulder the risk alone.
By forming an alliance, they are signaling to the market, to policymakers, and to energy companies, we believe hydrogen is structurally necessary for long-haul freight, and we are committing to standardizing the technology.
It reduces the technology risk for everyone involved.
But if you zoom in on the actual fleet operators, the logistics companies that have to buy these vehicles, the sheer uncertainty of this two-horse race must be paralyzing. Imagine being a logistics executive.
It's a nightmare. The upfront capex for a zero-emission truck, whether it's battery or hydrogen, is vastly higher than for a standard diesel rig. But more importantly, the residual value of the asset is completely unknown.
That is the crux of the adoption barrier, right? Fleet economics rely heavily on residual value. A company buys a diesel truck, runs it for 5 years, and knows with near certainty what they can sell it for on the secondary market to recoup capital.
With a zero-emission truck, they have no idea what a 5-year-old heavy-duty battery or fuel cell will be worth, or how much it will have degraded. The risk of the asset depreciating to zero is entirely on the fleet operator's balance sheet.
Which is driving a fascinating evolution in business models, outlined in the research as truck as a service, or TaaS. Because the freight companies are terrified of that residual value risk, the manufacturers are having to fundamentally change how they sell their products.
It is a profound shift in the value chain. OEMs are realizing that to force adoption in a conservative, low-margin industry, they have to absorb the technology risk themselves.
How does that work in practice?
With truck as a service, the OEM says to the logistics company, don't buy the truck. We will retain ownership of the physical asset on our balance sheet. We will handle all the complex maintenance. We will even partner with energy providers to guarantee your charging or refueling infrastructure.
And in exchange,
You just sign a contract to pay us a flat, predictable rate per kilometer driven.
it transforms a massive, risky CapEx investment for the fleet operator into a predictable, stable OpEx line item. The OEM transitions from being a manufacturer selling metal to being a service provider selling guaranteed uptime.
Exactly. But even with ties mitigating the financial risk, the underlying strategic dilemma remains. If a logistics network commits to battery electric, they are betting their operational survival on the assumption that megawatt charging infrastructure will become ubiquitous and reliable nationwide.
And if they commit to hydrogen, they are betting that the cost of green hydrogen fuel, which is currently exorbitant, will plummet rapidly as production scales. It feels very reminiscent of the HD-DVD versus Blu-ray format war, but with the entire backbone of the global supply chain at stake.
And what's becoming clear is that, unlike Blu-ray, there might not be a single monolithic winner. We are likely looking at regional fragmentation based on local grid capacities, political subsidies, and proximity to green hydrogen production hubs.
But as complex as the highway freight battleground is, it actually looks relatively predictable compared to what happens when we take these machines off the pavement.
Oh, absolutely.
When we move into the dirt, the rock, and the extreme environments of heavy industry, the technology split becomes even more extreme. Let's talk about the electrification of surface mining, heavy construction, and agriculture.
If you thought long-haul trucking was a brutal environment for a battery, surface mining is the ultimate stress test. We are talking about continuous 24-hour-a-day duty cycles, extreme multi-hundred-ton payloads, massive elevation changes, constant vibration, dust, and extreme temperature fluctuations.
The dossiers dive deeply into Caterpillar's strategic roadmap here, and it is a perfect illustration of how companies are hedging their technology bets. Caterpillar recently launched a fully battery electric version of their 793 mining haul truck.
But simultaneously, at the exact same time, they're heavily piloting 100% hydrogen-fueled reciprocating internal combustion engines for their industrial applications.
If you're looking through the consumer EV telescope, this looks like corporate indecision. It looks like they don't know which way the wind is blowing.
But when you apply the TCO framework and look at the physics, it is a highly calculated, ruthlessly pragmatic differentiation strategy.
Caterpillar understands that a battery might work perfectly for a compact wheel loader on a city construction site.
Or, as we discussed earlier, an underground loader where you want to eliminate ventilation costs. The battery excels in those specific niches. But a 300-ton surface mining haul truck, that is a different beast entirely.
Right, these trucks operate in deep, open-pit mines, hauling hundreds of tons of ore continuously up incredibly steep, miles-long grades.
The energy density requirement to move 300 tons of rock up a 12% grade continuously is astronomical. If you tried to power that exclusively with current lithium-ion technology, a battery large enough to complete a meaningful shift would be so large and so heavy that it would consume a massive portion of the truck's hauling capacity.
It's the ultimate payload penalty. You're spending millions of dollars on a mining truck just to haul its own battery up the hill rather than the ore that actually pays the bills.
Exactly. So for those absolute extreme duty cycles, Caterpillar is developing hydrogen combustion engines. Hydrogen gas carries the massive energy density required.
And an internal combustion engine is a known, durable technology that can withstand the vibration and dust of an open-pit mine far better than sensitive fuel cell membranes.
They are matching the specific molecule or the electron to the physical reality of the mission.
But the research highlights another variable in this off-road transition that is often completely overlooked. We obsess over the technology, battery chemistry, hydrogen compression, TOS models, but we forget about the human being sitting in the cab.
The dossiers include a case study from a modular mine care system deployed at a surface mine in Brazil, and it is a brilliant illustration of how human psychology impacts the energy transition.
The Brazilian mine case study perfectly demonstrates why hardware alone won't solve the emissions problem. It has to be paired with digital optimization.
This particular mine operated a fleet of 72 massive haul trucks, each capable of carrying 240 tons of material. The mine managers were analyzing their operational data and noticed massive, inexplicable spikes in fuel consumption, specifically during the dumping cycle. When the truck has reached the top of the pit and is lifting its bed to dump the ore into the crusher, they sent engineers in to pull the telemetry data from the machines to find out why.
And what the data revealed wasn't a mechanical flaw, it was pure human habit. The truck operators were heavily pushing the accelerator pedal while the hydraulic bed was raising to dump the load.
You have to put yourself in the driver's seat. You're operating this colossal, isolating machine. You pull up to the crusher, you engage the hydraulic lift, and it takes 20 full seconds for the bed to fully rise.
20 seconds feels like an eternity when your performance is judged on cycle times.
Exactly. And the operators' brains, trained on decades of older internal combustion logic, told them, if I rev the engine, I will generate more hydraulic pressure and the bed will raise faster. So they buried the throttle.
But the digital telemetry data proved that this intuition was completely false. The newer hydraulic systems were governed by software. The bed raised in exactly 20 seconds whether the engine was resting at a normal idle or fully revved to the maximum.
Pushing the pedal did absolutely nothing for productivity, but it did something catastrophic to the mine's operating expenses.
The telemetry showed that by unnecessarily pinning the throttle, the engine speed jumped from an idle of 1,500 RPM up to 1,900 RPM. And that simple human action caused fuel consumption to skyrocket from roughly 74 liters per hour to over 134 liters per hour during that part of the cycle.
They were burning nearly double the fuel for zero gain in operational speed.
By identifying that specific behavior through data and then implementing a digital lockout or retraining the operators, the mine saved an estimated 83,000 liters of diesel fuel annually.
That translates to a direct operational cost savings of up to $335,000 a year, just by stopping operators from unnecessarily revving the engine for 20 seconds per cycle across the fleet of 72 trucks.
It's incredible. It's like a company spending tens of millions of dollars to perfectly insulate a corporate headquarters with state-of-the-art materials, but leaving all the windows wide open in the middle of a blizzard.
Sometimes the biggest, most cost-effective technological leap in an energy transition isn't a new battery chemistry. It's using data to correct legacy human habits.
And the major equipment manufacturers are acutely aware of this human variable. They know they have to design systems that optimize efficiency regardless of operator behavior. That's why the research highlights Caterpillar's upcoming dynamic energy transfer, or DET, system.
Which is slated for commercial availability in late 2026.
How does the DET system bypass that human element?
It is essentially a modernized, highly flexible trolley assist system. It's a localized infrastructure network built into the steepest grades of the mine. As a truck, whether it is diesel electric or battery electric, approaches the steep incline, it connects to a physical overhead or rail power line.
Oh, wow.
The DET system seamlessly transfers massive amounts of grid energy directly to the truck's wheel motors while it is moving.
So instead of relying on the onboard battery or the onboard diesel engine to fight gravity, the truck pulls power directly from the local microgrid.
Exactly. It bypasses the onboard energy storage constraints entirely during the most energy-intensive part of the cycle. It allows battery trucks to operate with smaller, lighter battery packs, reducing the payload penalty.
And it takes the variability of human acceleration habits out of the equation. It's an ecosystem-level solution to a physical constraint.
Exactly.
So we've mapped out the domains where batteries win easily, where they face severe economic headwinds on the highway, and how off-road environments require a mix of alternative fuels and digital optimization. But now we have to push our investigation to the absolute boundaries of the global economy.
The environments where lithium-ion batteries are categorically, physically ruled out by the laws of thermodynamics. We have to look at the ocean and the sky.
Deep-sea commercial shipping and long-haul commercial aviation. These two sectors are governed by an absolute insurmountable energy density barrier.
It is not a matter of waiting 5 or 10 years for solid-state batteries to get incrementally better. Current and foreseeable electrochemical battery technology simply cannot power a multi-week duty cycle for a massive container ship traversing the Pacific Ocean, or a fully loaded passenger jet flying from London to Tokyo.
The sheer mass of the batteries required would exceed the buoyant capacity of the ship or the aerodynamic lift capacity of the aircraft.
Precisely. In these hard-to-abate sectors, the relevant strategic competition is completely divorced from electrification. It is exclusively a race to develop and scale sustainable liquid and gas molecules.
Let's examine the maritime shipping sector first. The logistics industry is actively pivoting away from heavy bunker fuel, and the research highlights two primary contenders to replace it.
The two molecules dominating maritime R&D right now are e-methanol and green ammonia. They have very different operational profiles. E-methanol is currently in the lead in terms of commercial scaling.
Major shipping conglomerates like Maersk are already ordering and launching dual-fuel vessels capable of running on it. Strategically, e-methanol is attractive because it is a liquid at ambient temperature.
Which means it is relatively straightforward to handle, transport, and store using slightly modified versions of existing maritime bunkering infrastructure. It doesn't require extreme pressurization or cryogenic cooling.
The challenge with e-methanol is sourcing the sustainable carbon required to synthesize it, which makes scaling production expensive.
Then you have green ammonia, which the dossiers classify as pre-commercial but strategically vital. Ammonia is fascinating because its chemical formula, NH3, contains no carbon at all.
When you burn it or run it through a fuel cell, it produces zero CO2 emissions. And it has a higher volumetric energy density than liquid hydrogen,
Well,
but it comes with a massive operational caveat.
it is highly toxic. An ammonia leak on a massive container ship in the middle of the ocean, or worse, in a densely populated port city, is a catastrophic safety hazard.
Using green ammonia requires completely redesigning the safety protocols, the ventilation systems, and the engine designs of the global fleet.
It is a genuine high-stakes race to see which molecule, the easier-to-handle methanol or the carbon-free ammonia, will ultimately become the dominant bunker fuel of the 2030s.
And while the maritime industry debates methanol versus ammonia, the aviation sector is locked into its own specific pathway.
In commercial aviation, the dominant near-term strategic pathway is overwhelmingly sustainable aviation fuel, or SAF. SAF is essentially a synthetic or bio-based hydrocarbon that chemically mirrors traditional Jet A fuel.
The strategic brilliance of SAF is that it is a drop-in replacement, meaning you don't have to redesign the airplane.
Exactly. You can blend SAF with traditional jet fuel and burn it in existing Rolls-Royce or GE jet engines today, utilizing the exact same airport refueling pipelines and tanker trucks. It bypasses the infrastructure bottleneck entirely.
But the massive hurdle for SAF is pure economics. It is currently several times more expensive to produce than fossil jet fuel, and the global supply of sustainable feedstocks like used cooking oil or agricultural waste is physically constrained.
What about hydrogen planes? You see startups and even major players like Airbus heavily promoting concepts for hydrogen-powered commercial aircraft.
Hydrogen aviation, whether using liquid hydrogen to power fuel cells for propellers or combusting it directly in modified jet engines, remains highly speculative. The energy density of hydrogen by weight is fantastic, but by volume, it is terrible.
To carry enough liquid hydrogen for a long-haul flight, you have to completely redesign the aerodynamics of the aircraft to accommodate massive, heavily insulated cryogenic fuel tanks.
It is a fundamental reinvention of aerospace engineering, and while it may have applications in short-haul flights sooner, it is likely decades away from wide-scale commercial reality for transcontinental routes.
This inherent scarcity of green fuels, the limited supply of SAF, e-methanol, and green hydrogen, brings up a critical macroeconomic concept introduced in the research by the International Transport Forum, or ITF.
It's a framework called the Merit Order of Energy Allocation. It sounds deeply academic, but it is actually one of the most practical, vital tools for any policymaker or investor navigating this transition.
It is essential because it acknowledges reality. Green energy is scarce. We do not have an infinite supply of renewable electricity, and we certainly don't have an infinite supply of the green synthetic fuels derived from it.
Therefore, a global economy has to prioritize who gets to use those scarce resources to achieve maximum decarbonization. The ITF Merit Order establishes 3 fundamental rules for managing this scarcity. Let's walk through them, because they dictate exactly where capital should flow.
Rule 1. Prioritize direct electrification for road and rail transport wherever physically possible.
The logic here is pure thermodynamic efficiency. If you take renewable electricity from a wind turbine and send it directly over the grid to charge a battery in an urban delivery van or a passenger car, you utilize roughly 80 to 90% of that original energy.
It is the highest possible return on investment for a green electron, which leads directly into Rule 2. Avoid using hydrogen and e-fuels for cars and light trucks if a battery can do the job.
Because of the massive energy penalties we discussed earlier. If you use that same wind turbine to power an electrolyzer to make hydrogen, compress the hydrogen, transport it, and run it through a fuel cell in a passenger car, you have lost over 60% of the original energy as waste heat.
It is a colossal waste of scarce renewable energy to use complex molecules in environments where simple electrons will suffice.
And that culminates in Rule 3. Reserve sustainable bioenergy and e-fuels strictly for the hard-to-abate sectors.
This is the crux of the global strategy. We must purposefully restrict the use of scarce liquid fuels like SAF and green methanol to long-distance aviation and deep-sea maritime shipping. Why? Because, as we established, those sectors have literally no other technological option.
If a corporate logistics giant buys up all the limited green methanol in the market to run a fleet of short-haul delivery trucks, which could have easily been electrified, they leave the shipping and aviation industries stranded with no viable decarbonization pathway.
The merit order is about macro-level allocation to ensure the entire global supply chain can transition.
But practically speaking, how does a multinational logistics corporation actually execute this strategy? Because the physical reality of the global supply chain is incredibly messy.
The dossiers describe a mechanism called a book and claim certification system, utilizing standards like ASTM D975 for fuel specifications and ISCC Plus for sustainability certification.
I have to admit, when I first read about how book and claim works, it felt incredibly suspicious to me.
It is a concept that faces heavy scrutiny. And at first glance, it absolutely looks like corporate accounting magic.
Right. Because the book and claim system allows a logistics company to purchase the environmental attribute of a green fuel, even if the physical green fuel they paid for goes into a completely different ship halfway across the world.
So a massive corporation can proudly claim to their shareholders that they are shipping their goods green, while their actual physical cargo is loaded on a ship departing from South America that is burning heavy, dirty bunker fuel, simply because they paid for green methanol to be used in Europe.
How is that not just greenwashing?
I completely understand why it looks that way. But to understand why book and claim is not only legitimate but structurally vital, you have to look at the chicken and egg problem of early infrastructure scaling. Let's trace the economics.
Okay.
Right now, producing green methanol requires specialized multi-billion-dollar facilities. These facilities only exist in a few localized hubs, primarily in Northern Europe.
Okay, so the supply is geographically highly constrained.
Precisely. Now, imagine a global consumer goods company wants to invest millions of dollars to decarbonize its supply chain. But its manufacturing base and its shipping routes operate entirely out of South America and Southeast Asia, where there is currently zero green methanol physical infrastructure. Under a rigid physical tracking system, what can that company do?
Nothing. They're geographically locked out of the transition until someone builds a pipeline and a bunkering facility in their specific port.
Exactly. The capital is stranded. The book and claim system decouples the financial investment from the physical supply chain constraints. Through highly audited frameworks like the ISCC Plus certification, the consumer goods company in South America can pay the financial premium for green methanol.
That premium is injected directly into the European production hub, allowing it to scale its operations. The physical green methanol is pumped into a European vessel, displacing fossil fuels there.
So the net reduction of carbon emissions in the global atmosphere is identical. The atmosphere doesn't care where the carbon was reduced.
But crucially, the book and claim mechanism acts as a financial bridge. It allows capital from all over the world to pool and fund the nascent green fuel industry immediately, driving down the cost curve, rather than waiting decades for physical bunkering infrastructure to reach every port on Earth simultaneously.
The rigorous auditing ensures the green fuel was actually produced and consumed once, preventing double counting.
That reframing makes complete sense. It's a mechanism to aggressively pump liquidity into a nascent market. So as a corporate strategist, when you zoom out and look at this entire chaotic map we've drawn, batteries dominating the city and underground mines, hydrogen fighting for long-haul freight, e-methanol for the oceans, SAF for the skies, and complex financial mechanisms tying it all together, it requires a fundamentally different mindset than the historical automotive playbook of we build gas cars and now we build electric cars.
It requires a profound strategic shift from monolithic manufacturing to ecosystem management. And this brings our investigation directly back to our central motivating question. Where do governments, massive institutional investors, and legacy industrial companies actually place their bets for the next 20 years?
The strategic dossiers dedicate a significant portion of their analysis to evaluating what they term the Toyota wager. For the better part of a decade, Toyota, the largest automaker in the world, has faced intense, often blistering criticism from environmental groups, tech investors, and the mainstream media for pursuing a multi-pathway strategy.
While competitors were declaring they would be 100% battery electric by 2030, Toyota was simultaneously investing heavy R&D capital into traditional hybrids, plug-in hybrids, battery electric vehicles, and hydrogen fuel cells. The prevailing narrative painted them as a dinosaur, paralyzed by indecision and dragging their feet into the future.
But when you synthesize everything we have discussed today, the brutal reality of the payload penalty, the fragility of local grid transformers, the variable costs of charging infrastructure, and the ITF merit order, the strategic dossiers argue that Toyota's approach is not indecision at all. It is, in fact, a highly rational, structurally sound competitive advantage.
This is where the entire deep dive clicks into place. The multi-pathway thesis acknowledges a fundamental truth that the telescope effect obscures. The future of global transport is differentiated by physical application, not by a single monolithic technology.
If you are a niche startup selling premium passenger cars in California, you can absolutely bet your entire enterprise on a pure BEV strategy. But if you are Toyota or Caterpillar or the Volvo Group, if your mandate is to build machines for incredibly diverse, rugged global markets from urban commuters in Tokyo to long-haul logistics routes across the Australian outback to off-grid agriculture in sub-Saharan Africa, betting your entire balance sheet on a single technology pathway exposes you to massive existential structural risk.
By pursuing the multi-pathway strategy, these industrial giants are building the internal capability to match the powertrain directly to the physical and economic reality of the customer's specific application. They are mitigating technology risk through diversification. But beyond the physics, there is another layer of risk driving this strategy, and it is entirely geopolitical.
The transition from internal combustion to electrification is fundamentally a shift from extracting liquid fuels to extracting and processing critical minerals. And the geopolitical reality, as outlined starkly in the dossiers, is that China currently holds a massive, deeply entrenched lead in battery cell manufacturing, raw material processing, and sheer scale-driven cost efficiency.
It's a structural advantage built over more than a decade of highly coordinated aggressive industrial policy. The research indicates that Chinese OEMs can produce battery electric vehicles at a cost base that Western legacy automakers simply cannot match in the near term.
So what is the strategic playbook for Western automotive and industrial companies? Because engaging in a direct price war on mainstream BEVs seems like financial suicide.
The dossiers offer a very clear strategic recommendation for Western OEMs. First, abandon the volume price war in the entry-level BEV space. You cannot win a race to the bottom against a heavily subsidized, hyper-optimized supply chain. Instead, retreat and defend the premium and commercial segments where brand heritage, reliability, and driving dynamics still command a significant profit margin.
And then redirect that capital into software.
Exactly. Invest heavily in software-defined vehicle architectures, advanced autonomous features, and connected fleet services. The physical battery cell is increasingly becoming a commoditized component. The differentiation and the margin will be found in the digital ecosystem that manages the vehicle. Furthermore, the recommendation is to partner aggressively for battery technology rather than burning billions trying to replicate a mature supply chain from scratch.
But securing that supply chain brings up the final, perhaps most critical, back-end challenge of the electrified transport economy. We have to talk about the circular economy and the looming crisis of e-waste. The International Energy Agency projects that there will be roughly 145 million electric vehicles on the road globally by 2030.
That represents a staggering volume of highly complex, chemical-heavy, physically massive lithium-ion batteries that will eventually degrade and reach the end of their useful life in a vehicle.
If we simply treat these degraded batteries as waste, the entire transition fails both environmentally and economically. Securing the supply chains of the 2030s and 2040s requires addressing the end-of-life challenge immediately. The industry relies on a strict waste hierarchy: prevention, reuse, refurbish, recycle, and only as an absolute last resort, disposal.
The reuse phase is fascinating because a battery that is considered dead for automotive purposes isn't actually dead. When an EV battery degrades to roughly 70% of its original capacity, it no longer provides the range required for a car. But 70% of a massive battery is still a tremendous amount of energy storage.
Which is why the immediate secondary market for these packs is stationary grid storage. You take the refurbished batteries out of the cars, stack them in shipping containers, and connect them to the local distribution grid. They act as massive buffer systems, storing cheap solar or wind energy during the day and discharging it during peak evening hours.
Ironically, the degraded batteries of the first generation of EVs will be used to stabilize the grid to allow the second generation of EVs to charge without melting the transformers we discussed earlier.
But eventually, even in a stationary application, the chemistry fails completely. They do die. And when they do, we desperately need the metals locked inside them back. This is where the dossiers delve into the science of recycling, specifically contrasting pyrometallurgical and hydrometallurgical innovations.
These two processes represent vastly different approaches to the circular economy. Pyrometallurgy is the older, more brute force method. It relies on high-temperature smelting. You essentially throw the battery modules into a massive furnace and burn them down. It is highly effective at recovering heavy metals like cobalt and nickel, which settle into an alloy at the bottom,
But there is a massive drawback to the furnace,
the
right?
critical drawback. Pyrometallurgy is incredibly energy-intensive, generating high emissions, and crucially, the intense heat burns off the graphite and, most importantly, the lithium, which is lost in the slag. In a world desperate for lithium, pyrometallurgy destroys the most sought-after component.
Which is driving massive investment into hydrometallurgy. When I was looking into how this works, it sounds almost like science fiction. You take this massive, dead, potentially dangerous battery pack, you completely discharge it, and then you physically shred the entire thing into what the industry literally calls black mass.
It looks exactly like it sounds, a dark, powdery mixture of all the internal components. Hydrometallurgy avoids the furnace entirely. Instead, it uses aqueous cameramo. You take that black mass and run it through a complex series of chemical baths, acids, and solvents. Through a highly controlled process called selective precipitation, you continuously tweak the pH levels of the liquid.
So at one pH level, the cobalt dissolves and drops out of the solution to be collected. You tweak the chemistry again, and the nickel precipitates out. And finally, you extract pristine, high-purity lithium.
Exactly. Hydrometallurgy recovers a much higher percentage of the critical minerals, including the lithium, with a significantly lower energy footprint than smelting. Scaling these advanced recycling technologies is not just an environmental imperative, it is a vital geopolitical and strategic necessity. The only way Western economies can insulate themselves against raw material shortages and geopolitical supply chain shocks in the 2030s is to view every single dead battery as a high-grade domestic mine for critical minerals.
So we have covered a massive amount of ground today. What does this all mean for the executive, the investor, or the policymaker? Let's pull all these threads together into a cohesive thesis. What the research overwhelmingly proves is that a genuinely electrified transport economy is not a monolithic future, where every single vehicle, from a pizza delivery scooter to a 300-ton mining truck to a trans-Pacific cargo ship, runs on a lithium-ion battery.
The future of mobility is a highly fragmented, highly specialized multi-pathway portfolio. It's an ecosystem where technology is dictated by the unforgiving laws of physics and the brutal realities of operating margins. Batteries will absolutely dominate urban environments where routes are predictable, payloads are light, and downtime for charging is an acceptable part of the business model.
But hydrogen will carve out a massive, highly lucrative domain in heavy, continuous, high-utilization freight, where operational speed and payload capacity are the sole drivers of profit. E-methanol and sustainable aviation fuels will govern the oceans and the skies, supported by complex financial mechanisms like book and claim to accelerate infrastructure development.
Therefore, the entities that will successfully navigate this transition and capture the most value are those who actively ignore the telescope effect. They look past the consumer driveway, they respect the structural physics of heavy transport, they rigorously calculate the payload penalties, and they acknowledge the true hidden costs of grid infrastructure and raw material supply chains. The transition will heavily reward those who embrace the complexity of a diversified portfolio, rather than those who bet their entire balance sheet on a single simplistic narrative.
And as we close this investigation, I want to leave you, the listener, with a final, provocative thought to mull over. Throughout this deep dive, we have focused extensively on the physical hardware of the transition. The battery chemistry, the fuel cells, the synthetic molecules, the grid transformers. But if the future of global transport genuinely requires this complex, fragmented, multimodal mix of electricity, hydrogen, and e-fuels, the most valuable asset in the global logistics network of the 2040s might not be the physical engine or the fuel itself.
It might be the digital brain. Imagine a highly advanced AI and software ecosystem that acts as the central nervous system for a massive global logistics corporation. an algorithm that dictates exactly which fuel a multimodal freight network uses on any given Tuesday. It dynamically analyzes real-time electricity pricing on local grids. It monitors localized weather patterns affecting wind turbine output. It tracks the spot price of green hydrogen and e-methanol, and it routes a shipping container seamlessly between a battery electric regional truck, a hydrogen-powered freight train, and a methanol-fueled cargo ship, constantly optimizing for the lowest possible cost and carbon footprint moment by moment.
The ultimate competitive advantage in that future won't just be the brute force of moving the physical goods. It will be mastering the immense algorithmic complexity of how to power that movement dynamically. The physical hardware becomes commoditized. The value shifts entirely to the software. The most critical strategic question becomes, who will build and ultimately control that algorithm?
Exactly. Who controls the brain that manages the molecules and the electrons?
It brings us right back to our initial realization. This is not a clean, neat historical break. It is not a simple one-to-one swap of a gas tank for a battery pack. It is a complete foundational rewiring of both the physical and digital infrastructure of the global economy. Thank you for joining us on this deep dive. We will see you next time.